Okay, AP students, welcome to a review over Big Idea 2. This will be, I think, like I said in the last one, into 9 big ideas, but this will be the second video of those 9. This one's going to be over molecular and ionic compounds and a little bit of Lewis dot structures, and we'll talk about some Morse potential graphs and such. So let's go ahead and get started here. Oops, there we go. So yeah, we're going to talk about molecular ionic compounds and those structures and properties of those. Let's start over here on the left. So I've got covalent compounds here. These compounds are composed of 2 or more nonmetals. These 2 or more nonmetals, let me see if I can get this to be the right color, are going to actually share electrons, pairs of electrons that form bonds between them. So there'll be bonding pairs of electrons. Bonds between 2 nonmetals, between 2 unlike nonmetals, will tend to create like a dipole. That dipole will be will be due to their difference in their electronegativity values, and I'm going to abbreviate electronegativity there. So something like hydrogen and chlorine, I'm drawing their dot structures here with 7 dots, would actually form a single bond between those 2. So it would be this overlap of these 2 electrons forming the bond, and I would draw it like HCl. And I would encourage you guys to include the lone pairs of electrons on the outside on every element, so you demonstrate that you understand and are doing the octet rule. These electrons here in this bond, if it were polar, would be pulled toward the more electronegative atom. So pulled to, the electronegative atom. So in this case, that's the chlorine. So there would be a dipole moment that was pulled towards chlorine, leaving the side that was hydrogen just slightly positive. If the electrons are shared equally, or the dipoles do cancel out, it goes all the way around, and the atom is symmetrical, or the molecule is symmetrical, then the molecule is going to be, in fact, nonpolar. Great example of that is, diatomic nitrogen would have 3 shared pairs of electrons, and then the 2 lone pairs on the outside that would cancel each other out. The dipole moment would be 0. Of course, in carbon dioxide, which would look like this, carbon dioxide would have a dipole moment on either side, with the electrons pulled closer to the oxygen atom, but it would actually, the dipole moments would cancel each other out on both sides. So this would in fact be also nonpolar. If electrons are shared unequally, or the dipoles don't cancel out, then those molecules are said to be polar. Yeah, so if you have something where the molecules aren't canceling out, a quick example, like chloroform here. So if I have CH3Cl, there would be more electrons pulled in this direction here, making the other ends positive, and this would have a dipole moment as a molecule. And so that molecule would in fact would be termed polar. So if I go down here to like the Lewis, let's go, and then we'll come back to Lewis structures. Let's go over and talk about metallic compounds first, and then we'll come back and revisit the rest of that. But metallic compounds, these are compounds that are composed of metal cations surrounded by mobile delocalized valence electrons. And so the easiest way to think of this is that sea of valence electrons, where electrons are kind of free to move about the metal atoms, but they're kind of embedded in between these metal cations. And this gives rise to a lot of different properties for metals. For instance, that they can be malleable or ductile. It also leads for them to be excellent conductors of electricity, because they have these transfer of electrons is so easy. So these electrons can lead to, like I just said, malleability and ductility. I think I spelled that right, ductility. And if there's a mixture of these, they're actually termed alloys. So if you have, say brass, or you have zinc and copper together, those things, that would be an alloy. There are 2 different types of alloys. There's substitutional alloy. This is where the radii of them are similar in size. I'll say close in size. And for interstitial, this is where the radii are are quite different. So they differ a great deal. One would be far smaller than the other. A good example of that would be steel. Do we have that? Yeah, we do have that example right here. So steel, you have, let me see if I can change this color real quick. You have the carbon atoms kind of placed in here in between each of these iron atoms. And so that it actually holds the steel together, or the iron atoms together better. But if you have, an improper ratio of those, it actually causes it to be more brittle. But anyway, so a substitutional alloy, it's got 14 karat gold there. So it's got gold and silver kind of mixed together. Notice that the size of these atoms, change color again. The size of these atoms here are roughly the same size. Okay, so they're kind of mixed together in there, different certainly than the interstitials. If I move over here, and we'll go and look at ionic compounds, and we'll go back to our drawings here, but these compounds are composed of ions that are held together by strong Coulombic forces. It's really an electrostatic attraction between them. I should put that in there too. This is really termed an electrostatic attraction for a positive and a negative attracted to one another. That means that compounds that are made of highly charged ions and those of really small ions are going to have stronger attractions due to that Coulombic force. I'll write it up here, but you remember Coulomb's law, I hope. KQ1 over KQ1 Q2 over the distance between those ions squared is how it is. So something like you have lithium fluoride and rubidium iodide. They both have the same charge, so charge won't be an issue here. But lithium's charge is +1, fluorine a -1, rubidium a +1, and iodine a -1 as well. But the difference here is the size. Lithium and fluorine are quite small, and rubidium and iodine are significantly further down the periodic table. They're in period 5, where the lithium and fluorine are in period 2. So this would be a much smaller denominator and therefore a much greater attraction between the two. Over here, we've got magnesium with a +2 and oxygen, with a -2, sodium with a +1, fluorine with a -1. So the magnesium oxide is going to be far stronger, that Coulombic force between the two, simply because the numerator of the Coulomb's law is going to be far greater. And generally, we say that the charge trumps the size. So charge is always going to be more important than the size, but size matters too. Okay, so formula units. Formula units are the base unit for this. So that the formula unit is just 1 negative and 1 positive, or 1 2 minus and 1 2 plus together. Just one lithium fluoride unit, a lithium and a fluorine, and that's it. Those are put together in unit cells. Unit cells will be kind of whatever that structure is, whether it's cubic, I'm kind of drawing a really bad cube here, or if they have an entire lattice work of them where you have several together forming that, whether it be a face-centered cubic. Actually, that would be a unit cell face-centered cubic cell, but this is showing the entire system here. That would be your lattice work. Lattice is arranged to maximize the attraction and minimalize the repulsion between them. So the negative ones will be as far away as they can from other negative ones while still attracting to those positive ions. So in this particular case, we've got chlorine atom plus 1 electron is actually going to give me that chloride ion, whereas sodium in this case as an atom is actually going to lose an electron. So we'll lose an electron and then also form this sodium ion. So let's go back to the Lewis structures I kind of said I would promise to go back to. They're down here on the bottom. What a Lewis diagram really is a model that represents in 2D, no less, unless you're really good at drawing and shading and stuff, representing bonding in covalent and ionic compounds. So for your ionic ones, if you had something like, let's do magnesium and oxygen. So if I added magnesium and oxygen together, in terms of their Lewis structures, magnesium would have just 2 dots in the, we tend to call this side over here the S, the P, the P, the P. It doesn't really matter. And then assign 1 in each of the P's as you go around it. It doesn't really matter what you do, but it would be best to pair them together. And then the oxygen, eraser off there, oxygen would have 2 in the S, and then 1, 2, 3, 4s in the P's, and I'd be left with those 2 there. If I were to draw this where these 2 came together in ionic bond, I would write Mg like this with no valence electrons around it with a 2+ charge, and oxygen with a full octet about it with a 2- charge. And it's just written like that. You don't need to worry about its direction or what it looks like that. It's really not necessary. If we did something that was a covalent compound, something that is molecular, SO3 is a good example, sulfur trioxide. If I drew out sulfur trioxide, I have 6 electrons from the sulfur, and then I have 3 × 6 electrons from the oxygen. That's giving me a total of 24 electrons. I'm going to kind of run out of room here, so I'm going to draw it down here. Actually, let me not do that in case you guys have room, because you're going to run out of room on the next part if I don't. So there we go. Let me lose that magnesium oxide. If I were to draw this, I would draw sulfur in the center, oxygens around every side, remembering how to do this, the process that is. Give everything 8, and then go and recount and see if I actually have 24 electrons. If I count right here, I've got 26. If I count by 8s, there's 3 8s on the outside, which is 24, and then the lone pair up here makes it 26. So 26 electrons is too many. What I would do is remove these 2 and then create a double, so 2 pairs, sorry. So I remove 2 from the sulfur and 2 from the oxygen on the right, and I'll make a double bond there and create that resonance structure. This would have multiple structures, of course, and I could redraw sulfur trioxide in 3 different ways. Don't draw your oxygens like rotating around it. Just move the double bond to each one. Keep the same sort of 3-dimensional structure you see. So oxygen on either side with 1 down below. Don't suddenly put 1 up on top if you have to draw resonance structures. But to draw these, for a Lewis dot structure for a covalent compound like I did already, count the valence electrons, arrange the atoms symmetrically around them, join them with 1 bond, and then go and fill your octets, and then of course a duet for hydrogen. Check to make sure you have the right amount. If you don't, create double or triple bonds as you may need. A Lewis diagram may demonstrate, like I said a minute ago, resonance. And for the sulfur trioxide, I guess I'll go ahead and draw it. I would have one like this, which is the one I have already drawn up there. Yeah. If I drew another resonance structure, sometimes you'll see these like in brackets, all 3 of them. I would draw arrows in between them and draw every single one of them. The only reason they would have brackets around each one would be if they had charge. Sometimes I've seen them where they draw brackets around all 3 resonance structures with a single charge on the outside. I would actually probably draw all 3. I'd be less likely to have issues or make a mistake. Anyway, but don't forget, if it is an ion, you've got to draw brackets and charge. If this were SO3 2-, it'd be done a little differently as far as your adding is concerned, but you would put that brackets and 2- charge on the outside of your drawing, okay, of your Lewis structure. A Lewis diagram may be justified with what is called formal charge. And it's been a while since we did that, right? But in formal charge, you may have multiple drawings of a structure, and you have to kind of figure out what they are when you go through them. So I'll go ahead and do my formal charge over here on this side here. Let me pause this just for a second. Sorry about that. Somebody's knocking at the door. Okay, so let's do an example of SCN-. So let's do SCN-. So SCN- could be drawn. The way you would see this on the AP test is they'll give you a couple of different drawings of the structures of those, and you would have to determine by formal charge which one is the correct structure. I don't think they would ask, excuse me, ask you, what is the formal charge of this atom in this compound? But they could, and you should be able to do that. So it could be drawn with sulfur, single bond to the carbon, and then a triple bond to the nitrogen, like so. Or perhaps it could be drawn with sulfur with a double bond to the carbon and a double bond to the nitrogen with a lone pair on both the sulfur and the nitrogen. If I went, oh, sorry, it wouldn't be a single lone pair. I've drawn this incorrectly, my bad. Should have all of the, that's correct. And then over here, I would have 2 lone pairs. Over here, I have 2 lone pairs. That's correct. So either of those 2 drawings could be correct. To do it by formal charge, what you'll do is you'll take the number of electrons that the atom actually has, valence electrons for that particular atom. So in the case of sulfur, that would be 6. And you will subtract from it the number of electrons that are represented in the diagram that are attached to sulfur. So in this particular case, sulfur has 8 electrons around it. But what we say is that half of the bond is sulfur is responsible for, and half the bond carbon is responsible for. So for that single bond between them, one of them is carbons and one of them is sulfurs. So in this case, sulfur, to calculate its formal charge, would be 6 minus 7. There are 6 that it brought to the compound, and then there are 7 that are drawn. So that would actually give me a formal charge of a -1 for that one. So this would be a -1 formal charge. Let me get rid of this. If I did the carbon brought 4 and it has 4 bonds. So 4 minus 4 for carbon, that would be 0. And if I go to the nitrogen, nitrogen has 5. It has 7. No, it doesn't have 7. How many does it have drawn? It has 2 plus 1, 2, 3. That's be 5. 5 minus 5 would be 0. And that would be a -1, which makes sense because each of these drawings for this thiocyanate ion is actually SCN minus. Some of you may be out there shouting, but I should have drawn brackets and charge around each one. I'm going to leave it off just for this formal charge experience, but yeah, I should have had that on there. Okay, if we go to this other one and check it out, sulfur has 6. I have 2, 4, 5, 6, 1 from each bond, so that'd be 6 minus 6 would actually be 0. Carbon, we're going to have 4 minus 4, which would be 0. And for nitrogen, I have 1, 2, 3, 4, 5, 6. Brought 5, it's in column 5, group 5, minus the 6 that are drawn, it would be -1. Now, the rules to determine whether formal charge is correct is, first off, it has to match the charge of the species that it is. If it were neutral, the overall charge would be 0. If it had a -1, like the SCN minus does, then it would overall have a -1. And if I add -1, 0, and 0 on each of these, I get -1, which is correct. But that negative charge needs to be on what we term the most electronegative element. So is sulfur or is nitrogen the most electronegative element? In our case, nitrogen is the most electronegative element, so this drawing would be the best drawing. One of the other things about formal charge is you want to minimize the amount of formal charge. So you want as few charges as possible that still give you the overall charge, in this case of -1. Now here we have the same minimal amount of formal charge. They both only had 1 charged species, but if you have one, sulfate is a good example, you may have all the atoms charged, and then in another drawing only have 2 or 3 of them charged. So it would be best, or the rule is, sorry, that you must have minimalized formal charge, so the smallest charged species, and that negative must be on the most electronegative element. There we go. Okay, so moving on. So over here on the left, we've got kind of a drawing showing you the overlap of some bonds here. This right here, yeah, it's called a sigma bond. Sigma bond is usually represented by, like, it looks like it's a sigma, but it's kind of like a backwards 6 or kind of like an A, whatever. This is a single sigma bond. A good example of a single sigma bond be like, ooh, that's a terrible drawing of chlorine, would be like Cl2. So chlorine to chlorine would just be a single bond and would have 1 sigma bond between them. And what a sigma bond is a direct overlap of s orbital electrons from one atom to the other. If we look over here at the other ones that are listed here, I've got pi bonds. And so in the case of a pi bond, you'd have something like oxygen or O2. It would have 1 sigma for the first bond and 1 pi for the for the second bond. Single bonds will only have a sigma bond. Okay. A double bond will have a sigma, trying to draw around, and a pi bond, and triple bond will have a sigma bond and 2 pi bonds. And so if I look at the drawing here for oxygen, this would be the pi bond up here, pi bond down here. The 2 of these together is 1 pi bond. I know that seems strange, but it's 1 pi bond. If I had a second pi bond drawn on here, like if I had something that was a triple bond, say nitrogen, I would have to show these other P-shaped orbitals over here with a pi bond kind of in the back and a pi bond in the front. That would be a triple bond. I know it looks like there's 5 bonds there, but there's really not. A p orbital, or sorry, a pi bond is actually above and below the plane of the sigma bond. Pi bonds are going to be weaker than single bonds. So as you go from a single bond to a double bond to a triple bond, it's a greater amount of energy, but it's not the same amount of energy as having 3 sigma bonds. So the pi bonds are going to be weaker than the sigma bonds. What we see here in this diagram here, and this showed up on the AP test a few years ago, and my kids were quite shocked, is that this is a Morse potential graph, and it's showing the lowest point is where the distance between the 2 atoms is most stable, or it has the lowest potential energy. And so this area right in here is exactly where they're supposed to be. So these here are going to be, I guess we'll say, just right. Yeah, they're put together just right. If it's way over here, they're way too close together. And if it's over here, they're too far apart. 2 is 2 O's. Pause 1 second. So, yeah, Morse potential graph. I've attached a video in the folder if you want to watch it. It's a former student named Travis Stebbins who went through and did a really good job explaining this for one of my AP projects we did after the AP test one year. And he goes through and talks about Morse potential graphs. And there is also a PhET simulation. If you go to, I think it's phet.org or phet.com, you can just Google PhET simulations. And if you go look for Morse potential graphs, you'll see them. And they have a little thing you can play with this, which is actually pretty cool. Does a great job of explaining it. But essentially, there is a point at which the repulsive and attractive forces kind of cancel each other out, and it shows the most stable state of that atom, which is down here on the bottom. So last thing here is VSEPR, which is not really the way it is. It looks like it says VSEPR, but it's VSEPR. It's valence shell electron pair repulsion theory. And basically that we're saying that regions of electron density are going to repel each other, or pairs of electrons are going to repel each other around a central atom, or in the case of just 2 of them, between 2 atoms. But it's a model used to describe that 3D shape of molecules. And so there's a page in Schoology, so you can go and look at all the angles and shapes. It's also in your notes that we had before. But anyway, just looking at a few of them, not all of them. But this this idea ties several different theories together. So it ties together discussing things in terms of sigma and pi bonds. It discusses things in terms of Lewis dot structures. It brings things together in terms of hybridization, whether something has the central element is hybridized a certain way. We're not going to talk about hybridization of exterior elements, or something like if you had methane. We're not really going to talk about the hydrogen on the outside, but we are going to talk about the central element. This central element is what's going to make a difference and dictate what's happening with its arrangement or 3D structure, its VSEPR shape. So if you look at something that's just 2 things attached together, so like Cl2, that would be a good example. So like Cl2, it doesn't have to just be 2 atoms though. We could also have hydrogen cyanide or HCN, right? That one would have a sort of a 180-degree bond angle between the 2. We would call this thing in the center sp hybridized. So it would have a linear shape and it would be sp hybridized. And I taught you guys to remember by using your hand, where your thumb is the S, and then each of these are P's, and then beyond the 3 P orbitals, you would have a D orbital. And what you do is just count those regions of electron density, meaning the places that you find electrons. Doesn't matter if there's 2 of them or 6 of them, just like this HCN right there. There are 2 regions of electron density, regardless of the fact that there are 8 electrons. And so look at that. If there are 2 regions of electron density, it will be sp hybridized, and it will be a linear shape. If there are 3 regions of electron density, a good example, easy example actually, would be like BF3, breaking the octet rule and only having 6 valence electrons about it, would look like this, and it will have a 120-degree bond angle between them, and that structure would actually be in a single plane, and it's called trigonal planar or 3-sided planar. You could, now there are several of these, and if you go back and look at the sheet, it'll have them all for you, but you can have sp2 hybridization with something that actually had a lone pair on it. But I'm going to go ahead and get through tetrahedral, and then I'll go back and talk just a little bit about the lone pairs. So here it's a 109-degree bond angle between them. The drawing here that I've got, oh, let's just erase it and I'll draw it again. Would be methane. So methane would look like this, right? I've got my, oh, you know what? I'm gonna have to do that again. Hope you guys are forgiving. Okay, so carbon with my hydrogens around like this. And it would be drawn in a two-dimensional way like this, but those are actually 109.5-degree bond angles between them in a tetrahedral shape. Its hybridization would be sp3 hybridize. And so these can have different shapes. So sp2 doesn't just have to be trigonal planar, it can also be bent. You know, if I had something, let's see, what can I do that's bent? I think SO2 is. SO2 looks like this with a lone pair there. That has 3 regions of electron density, but the bond angles would actually be less than 120 degrees. Okay, instead of being 120, if I had an atom there, that lone pair on top is going to spread those out, push those two down a little bit further, and cause the bond angle to be a little less than 120. For sp3 hybridization, you could have something like ammonia. Ammonia is NH3. So there's my NH3, and it has a lone pair. This would actually have bond angles that are less than 109.5. And if you remember, this drawing here would not be bent. It would actually be trigonal pyramidal. And that kind of covers what the AP test is going to ask you. There are ones that go beyond this. Breaches of the octet rule, structures up to octahedral. You should look over those in case something crazy happens, but generally speaking, this is about what you need to know for the AP test. Okay, guys, that concludes our Big Idea 2 review for molecular and ionic compounds. If you think that this is, there's some areas of this you need to go back and look at, go back to our notes and check and look at that. And I'll see you guys in the next video.